Hi there, welcome to this video. My name's John. I provide tuition for A-level maths, A-level further maths, including 6-term examination papers and mathematics admissions tests. Well, welcome to this video where we're going to take a look at logarithms. Why logarithms? Because they're interesting. And if you're doing A-level maths, then generally speaking, you'll need to know about logarithms. And I find that logarithms are something that a lot of A-level maths students kind of struggle with to a certain extent. However, this video is going to go into quite a bit of detail potentially about logarithms. So if you are looking for kind of the basic, just basic facts about logarithms to get you through, class test or through your homework assignment or something like that, this is probably not going to be the video for you to watch. It is going to go into a bit of detail. I'm going to start off with some basic ideas, but it's going to gradually develop into a more detailed treatment of logarithms, and it's really for people that are genuinely interested in learning about mathematics and want to know more about logarithms, because they are an important part of mathematics. And if you go on to university to do mathematics, you'll see just how important logarithms can be. Okay, so let's start out with how can we justify the introduction of these things called logarithms into mathematics. I mean, there's all different ways that we can introduce the concept of logarithms, but why might we actually want logarithms in the first place? Okay, so in a previous video, I've looked at exponentials. Or I've looked at the video is to do with laws of indices, but it also really goes through the development of exponential functions. Okay, how we can interpret things like expressions like 2 to the power of square root of 5 and things like this. And if we've got effectively if we've got a function like 2 to the power of x, how can we make sense of such a function? Okay, even though really it was laws of indices that I was focusing on, a byproduct of what I go through in that video is really a development of exponential functions, general exponential functions. So we're going to take that as our starting point. We don't have to do this. So what we're going to do here is we're going to start with exponential functions, take those for granted, take those as our starting point, and from those exponential functions develop our concept of logarithmic functions. We could go the other way. I might touch on it briefly in this video towards the end. I don't really want the video to get too long, too lengthy, and too involved. But you can start with the definition of a logarithm function, or in particular what we might call a natural logarithm function, and from that develop our concept of exponential function. And if we do it in the right way, then we get agreement whichever way we go, whether we start with exponentials and derive logarithms, or whether we start with logarithms and derive exponentials. If we do it in the right way, we can get agreement. Okay, so it's not done randomly. We don't just define a logarithm function any old how. It's done in a very particular way, and with a certain amount of hindsight. Okay, so we're going to start with exponential functions. What do I mean by an exponential function? I mean something of the form y equals a to the power of x. Okay, so one way to justify the introduction of logarithmic functions is to, let's say we've got an equation such as 5 to the power of x equals 8. I want to solve this equation. Okay, so how could I go about solving this equation? Well, if I'm just stuck with addition, subtraction, multiplication, division, extraction of roots, and raising to powers, none of this is going to help me here. Okay, none of these operations is going to be sufficient for me to make x the subject here. Okay, it doesn't matter how much multiplication I do, how many roots I extract, or anything like that. So, okay, where do I go from there? Well, I can either go for an approximate solution, through trial and error. So choose a value of x, maybe choose something like, I don't know, x equals 1.2. try to find 5 to the power of 1.2. There's a question then, how would I do that? Because presumably I'm probably going to need a calculator to do that. What if I don't have a calculator? But let's say I'm able to calculate 5 to the power of 1.2, and I find that it's either a little bit more or a little bit less than 8. Okay, then I can adjust, right? I can make 1.2, I can choose a value of x that's a little bit more, a little bit less, whatever I need to do. But I'm only going to end up with an approximate solution. I'm never going to find the solution to this equation. And when we're dealing with pure maths, we're talking about exact solutions. We're not talking about approximate solutions. We're going to do mathematics. Okay, to do mathematics, we need to be dealing with exact values. So I want to talk about the exact solution to this equation. I want to say that there is a number which solves this equation, and I want to be able to refer to it in an explicit way. Okay, so on the one hand, I want to rearrange this equation, okay, to make x the subject. So x is equal to something, some number. A number such that 5 to the power of x is equal to 8. So, okay, that's one thing that I want to do. I want to be able to rearrange the equation, but then I also want to be able to refer to this number, which is x. Okay, so there might be all different ways that we can do this, but we can just invent this new type of operation called a logarithm, and we can say, right, the number that I'm talking about here, x, we can write it as this, which you probably recognize. Okay, so on the one hand, this allows me, this gives me a way of rearranging this exponential equation, and it also gives me a way of referring to the number x, which is the solution to this equation. And as far as I'm concerned, this expression log to the base 5 of 8, which is how it's said, refers to a particular number. I might not know what that number is, in the sense that I don't know what its decimal representation looks like or anything like that. I just know that this is referring to a particular number. And that's all I need to know. From the perspective of pure mathematics, sometimes that's all I need to know, that this expression points towards a particular number. Whether I know what that number is or anything like whatever else I know about it is kind of beside the point. Okay, so generally, if I've got the equation a to the power of x equals b, okay, then I can rearrange this equation to x equals log to the base a of b. Okay, so just so you know, a in both cases, here in the exponential equation and here in the logarithmic equation, a is called the base. Okay, so it's the base here and it's the base here in the logarithmic. And we've also got x, which is called the exponent. Okay, we're not really going to be too bothered about that, but just so you know, it's called the exponent. Okay, so here we've got the exponent. So log to the base a of b is the number which satisfies the equation a to the power of x equals b. So from this we can say, for example, then that a to the power of log to the base a of b is equal to b. Okay, and therefore we can kind of interpret this as meaning that the a and the log to the base a cancel. Okay, if we want to think about it that way, which we can do. Okay, so that gives kind of a justification as to why we might introduce the concept of logarithm. But we can also look at it in terms of functions and inverse functions. Okay, so for example, I'm not necessarily going to go into all of the fine details with this. There might be some things that you'll need to think about that you'll need to take from this video and kind of think about for yourselves, make some connections in your own mind between various bits of information that I'm giving you. So, by the way, I'm just kind of talking here. I've got a couple of things written down that I want to make sure that I cover in this video, but by and large, I'm just talking about logarithms. There's no particular plan that I've got, so whichever direction I go in, I decide to go in. If you don't like the video, don't watch it. Okay, so let's say we've got now y equals, again, a to the power of x, and this is our f of x. Okay. So think back to when you did GCSE maths, maybe, and you were looking for inverse functions of a function. Actually, do you know what? Let's have a look at why we might actually have an inverse function here in the first, because there's no guarantee that we have actually got an inverse function. Right. So y equals a to the power of x. This is something that we understand already, hopefully, and we know what its graph looks like. Okay, and just for sake of argument, I'm going to assume that a is greater than 1, because I can't be bothered with all the different cases. So we're just going to assume that a is greater than 1, and therefore the graph of a to the power of x is going to look something like like this, right? Something like, maybe it's got a bit wavy towards the this end down here with the negative values of x. Never mind, it's only a sketch. That suffices for us. And we can see from the graph, kind of, although we don't need to rely on the graph to see these things, we can actually derive these properties through the algebraic properties of exponential functions. We can deduce that this f of x here is continuous and strictly increasing, or monotonic increasing. There's different ways that you can strictly increasing. That'll do for us. So what I mean by strictly increasing is larger values of x corresponds to larger values of a to the power of x. Okay. So as I move from in this direction along the x-axis, the value of the function, the value of a to the power of x, gets larger. Okay, so compare that to with, say a quadratic, where as you move along the x-axis, if it's a positive quadratic, then you'll kind of go down and then you'll go back up, for example. It's only on certain parts of the graph of the quadratic that the graph is strictly increasing or strictly decreasing. Okay, but on other parts, it depends which interval you look at. The graph might go down and then back up, for example. All sorts of things that can happen. But with an exponential function, it's always strictly increasing. So a result from real analysis, which I'm not going to go through in this video. It's not particularly difficult necessarily, but it does require a more detailed understanding of what it means for a function to be continuous. From this, we can deduce that there exists an inverse function, f inverse of x exists. It is continuous, and it is also strictly increasing. Okay. So when I say that you need a more thorough understanding of continuous, there are very precise definitions in mathematics of what it means for a function to be continuous. The kinds of definitions that you might come across at A level for what it means for a function to be continuous are nowhere near sufficient, unfortunately. So what I mean is you might be told at A level that a continuous function is one whose graph you can draw without taking your pen off the page. Well, there are plenty of in contemporary mathematics are considered continuous functions, and you've got no chance of drawing their graphs. It requires a much more precise definition. We won't get into that in this video. If you do want me to go through it at some point in another video, let me know. We can go through what it means for a function to be continuous. And it can get quite technical. But if you go to university to do maths, believe me, you'll do a ton on continuity because you've got no choice. You have, as a mathematician, you have to know about continuity in sufficient detail. Okay, so we know that there is a function, an inverse function. Okay, it exists, it's continuous, and it's strictly increasing. So again, think back to maybe GCSE or maybe some of the stuff that you've done at A level. What's the relationship between the graph of a function and the graph of the inverse of that function? The graphs are reflections of each other in the line y equals x. If you don't know stuff like this, by the way, make sure that you do know. These facts, these little bits of information do really come in useful. I might even make a video at some point about why that's the case, why the graphs are reflections in the line y equals x. Again, anything that you want me to make a video, just let me know. Okay, I can make a video on it. As long as it doesn't get too complicated. So, therefore, the inverse function, we can draw its graph. Right? And its graph is going to look like... Okay, draw the line y equals x in. Roughly like that. The inverse function is going to look something like this. Okay, so it's going to go through 1 on the x-axis. And because the exponential function has an asymptote, which is the x-axis, as you go along towards the negative end of the x-axis, then the graph of f inverse of x also has an asymptote, but this time a vertical asymptote. Okay, so this here is the graph of y equals f of x, which is a to the power of x. And this is the graph of y equals f inverse of x. Okay, so we know that we have an inverse function then. But then we need a way of kind of denoting it. Okay, so if we've got on the one hand y equals f of x, which is equal to a to the power of x, how are we going to write the inverse function? Well, we've already kind of touched on it. It's going to be log to the base a of x. Okay, that's the inverse function, and you can test this out. You can check it out. You can check that f composed with f inverse of x is equal to x, which in turn is equal to f inverse of f of x. This is what it means for a function to be an inverse function. Okay. Again, it's something that you may have come across at GCSE, and it is really important that you bear in mind these little things that you've learned along the way at GCSE, at A level, that sometimes seem quite irrelevant at the time. They're actually really important. And a lot of people really struggle with some of these basic facts. So what I've just been talking about the relationship between a graph of a function and its inverse function, the graph of its inverse function being reflections in the line y equals x. A lot of people don't know this. They don't grasp this. So what will happen is, in lessons, for example, a student might say to me, I can't remember what the graph of, say, the natural logarithm of x looks like. And I'll say, okay, then fine. So, do you know what the graph of e to the power of x looks like? And they'll say, yes. Okay, so can you draw it for me? And they'll draw it. And I'll say, right, okay, so bearing in mind that the natural logarithm of x is the inverse function of e to the power of x, can you now draw the graph of natural logarithm of x? And they can't do it, okay? Because it's not that they don't know these bits of information, it's just that they haven't managed to relate these bits of information to each other. And it's really important that you do this in maths. that rather than trying to remember miscellaneous facts, isolated facts, which is not a good way of learning mathematics, that you learn mathematics in a much more, I hate the word, but holistic sort of way. You see that the bits of information that you learn are related to each other. And the more that you understand those relationships between the bits of information, the more chance you have of succeeding, being successful in mathematics. There's no guarantees, obviously, but you're just learning random bits of information and they exist as these kind of separate islands of information in a sea of nothingness, you've got no way of going between bits of information. Whereas if you've got bridges, you've got a network that allows you to go between all of these bits of information, you see how they're connected, then you can, you know, what you will realize is that you know a lot more than you've been explicitly taught. Okay, you don't have to be explicitly taught everything. You will be able to logically deduce things, which is a very powerful skill to develop. Okay, so we can deduce some basic properties of logarithms then. Oh, by the way, there are some particular logarithms that you might come across. Now, in terms of pure maths, the only logarithm that pure mathematicians are interested in is the natural logarithm. Okay, so the natural logarithm is the inverse. It corresponds to the exponential function. So if we've got y equals e to the power of x, for example, where e is the number e, 2.718, whatever, that number, then the inverse of this is y. The inverse function is y equals the natural logarithm of x, and it's written lnx. But understand that this is just shorthand notation for log to the base e of x. Okay, so there's nothing different in principle between general logarithms, log to the base a of x, and natural logarithm. It's just got its own notation because it's such an important logarithm. Okay, so at A level you'll tend to use this ln x to represent natural logarithm. If you do go into university, you'll tend to just write log x because you won't deal with any other logarithms. You'll only deal with natural logarithm. But so that's the natural logarithm. So there is no reason to expect that the base of a logarithm is going to be a whole number. It could be any positive number. Well, maybe not one. But any positive number, except for one. I will usually restrict to natural logarithm because any logarithm can be written in terms of any other logarithm. Okay, so generally speaking, unless I've got a good reason for doing otherwise, I'll stick with natural logarithm. But if I do need to go for general logarithms, I'll try to avoid logarithms with a base that is less than 1. Okay, you can't have negative numbers as your base. Okay, and okay, so also you might see, for example, just log x, which at A level this would effectively mean log to the base 10 of x. So if you see log x without an explicit base mentioned, this can mean two things. It can mean either the base is not important for the particular context in which you're working, or it's log to the base 10. Okay. Again, it's just special notation. And that's for A level. Once you get to university, generally speaking, log x will represent the natural logarithm, but not usually at A level. So a logarithm always has a base, even if it's not explicitly written. And how will you know whether when you see log x it means log to the base 10x, or whether it just means that the base is not important? Well, the context. You have to be able to read the context. If you can't read the context and understand the context, then, well, that's just unlucky, right? Because a lot of things in mathematics you have to deduce from the context. The meanings of certain things you have to deduce from the context. So for example, we take x in a certain expression. Is x a variable? So if I write, for example, y equals x cubed plus 3. And on the other hand, I might write x cubed plus 3 equals 11. Okay. In the first case, x is a variable. Okay. X is a variable. X can take whatever value. In the second case, here, x cubed plus 3 equals 1, x is an unknown, but it corresponds to a fixed number, which is 2 in this particular case. It happens to be 2. Okay. How am I supposed to know whether x is to be interpreted as a variable or whether it's to be interpreted as a fixed number? The context. I have to understand the context. If I don't understand the context, then I can't make those decisions. So that's your job, to understand the context. Okay, so we understand then what we mean by logarithm. We've come across some of the different types of different logarithms that we're likely to encounter. So just to be clear then, if we've got the expression a to the power of x equals b, this is true if and only if x is equal to log to the base a of b. Okay, so we can understand these two expressions, a to the power of x equals b on the one hand and x equals log to the base a of b on the other hand, as containing basically the same information. Okay, they contain the same information, but they just represent that information in a different way. In the same way, for example, if I've got, I don't know, 5x equals 21. This is one way of representing this information. Another way is to say x equals 21 over 5. Okay. I mean, this latter I might consider to be the solution to this equation 5x equals 21, but effectively the expression 5x equals 21 is expressing, it's saying that number which when multiplied by 5 equals 21. But that's what the second expression says. X equals 21 over 5 is also the number which when multiplied by 5 is equal to 21. Okay, so it's just different ways of representing the same information. Okay, so once we've established this, then we can start to think about what might some of the properties of logarithms be. So we've already seen that because the graph of the logarithm goes through through 1 on the x-axis, okay, then what that implies is that log to the base a, and irrespective of the base here, log to the base a of 1 is equal to 0. Okay. We can also deduce the following. Since we know that a to the power of 1 is equal to a, so thinking about comparing that with this, and now rearranging this using this implication, then I get that 1 is equal to log to the base a of a. Okay, so these are two useful bits of information. And something else that I really want to mention as well. There's a really common misconception with A-level students about how to interpret something like log to the base 3 of 5, for example. A lot of people will think of this as some kind of multiplication. They'll think about it as maybe log to the base 3 times 5. Which it's not, okay? We understand multiplication. Now, there's different types of multiplication within mathematics. Different operations that we might call multiplication, but there is one type of operation called multiplication that involves multiplying numbers together. Okay, two numbers. And it's the multiplication that you learned when you were, 5, 6 years old. That multiplication. Yes, there might be we might be able to multiply matrices, multiply whatever things. But we call these multiplications, but they're not multiplication of numbers. It's not the same operation. Okay, so when people think about log to the base 3 of 5 as multiplication, what they've got in mind usually is the multiplication between two numbers. But I can't if I try to multiply two things that are not numbers in the way that I multiply two numbers, it doesn't make any sense. I can't multiply a badger by an elephant, for example. It's madness. I mean, what on earth does that even mean, right? Similarly, if I try to multiply, in inverted commas, log to the base 3 by 5 using the multiplication that we understand between numbers, it doesn't make sense. It's not a multiplication. Log to the base 3 is not a number, it is a function. Okay, log to the base 3 of 5 is a number, and it refers to a specific number. And this may be another thing that people really struggle with is understanding that this expression, log to the base 3 of 5, is a symbol used to represent a number. Okay, in the same way that this symbol represents a number. It represents the number 3. Okay. It's just log to the base 3 of 5 is a more complicated number than 3 in a certain sense. Okay. But it's not a multiplication. So when you've got a logarithmic equation, so let me give an example. Let's say I've got something like log to the base 3 of x equals 7. Maybe not 7, because that's going to be a huge number, isn't it? Equals, I don't know, 2/3. Whatever. Who cares? And I ask some people to solve this equation. What they really need to be understanding is what I've already kind of pointed out, this equality, this implication between a to the power of x equals b if and only if x equals log to the base a of b. This tells you how to rearrange this equation. But people will think, oh, I can just divide through by log to the base 3. Okay? Well, no, can you divide through by a toothbrush? No. Doesn't make any sense. So it's not a multiplication. I'm sorry to kind of go on so much about it, but it is such a common mistake that people make when it comes to dealing with logarithms. Log to the base 3 of x. Log to the base 3 is a function. Okay. Hope that's understood. Right, so then we can start to think about some further properties of logarithms. So we've already seen, for example, that a to the power of log to the base a of b is equal to b. Okay. So, okay, let me change the b to x. And correspondingly, we get a to the power of log to the base a of y is equal to y. Okay, so therefore, I get that a to the power of log to the base a of x times a to the power of log to the base a of y is going to be equal to x times y. Now I've got my laws of indices. We're taking those for granted, by the way. Laws of indices. So I can use my laws of indices here to get a to the power of log to the base a of x plus log to the base a of y is equal to x, y. Okay, now going back to our little fact that a to the power of x equals b if and only if x equals log to the base a of b. Using this, I get that log to the base a of x plus log to the base a of y is equal to log to the base a of xy. Okay, and this you might recognize is one of our laws of indices, laws of logarithms. Okay, which is easy enough. Okay, so we can also do the following. Hopefully I'll get this right. So we've got a to the power of log to the base a of x, again, equals x. So let me just create a bit more space here. So that means that a to the power of log to the base a of x to the power of n is equal to x to the power of n. So therefore, again, using laws of indices say that a to the power of x to the power of y is equal to a to the power of xy. So using that here, I get that a to the power of n log to the base a of x is equal to x to the power of n. So therefore, n log to the base a of x is equal to log to the base a of x to the power of n, which you can recognize again as another one of our laws of indices, laws of logarithms. So what we're doing here is we're just proving the laws of logarithms, which, even though you don't necessarily need to know them for your A-level maths, if you are interested in maths, in mathematics, really developing your understanding and your knowledge of mathematics, then I would highly recommend that you have a go at proving the laws of logarithms, that you understand how they can be proved. Okay. What else is there? Oh, there's the change of base rule for logarithms. So you might have seen this. I'll just state it first. So if we've got, for example, log to the base x of y, then this is equal to log to the base a of y over log to the base a of x. So I said earlier in the video that any logarithm can be expressed in terms of any other logarithm. It's this rule that tells me that. So this is called the change of base rule. Why is it called the change of base rule? Well, look what's happened. The base here is x. The base here is a. Okay? I've literally changed the base. So what is a? Where does it come from? I decide what a is going to be. Usually based on the context. So I will choose, if I want to use the change of base rule, presumably there's a reason why I want to use it, and I will choose the base that is the most convenient for me to use. Okay? So for example, log to the base 5 of 7 is equal to log to the base 10 of 7 over log to the base 10 of 5. It's also equal to log to the base 17.2 to the base 7 over log to the base 17.2 of 5. It's also equal to the natural logarithm of 7 over the natural logarithm, and so on and so forth. Right? So this can be a really useful rule to use, and this that really implies that we don't even need to bother, as pure mathematicians, we don't really even need to bother with other types of logarithms other than the natural logarithm, because any logarithm can be expressed in terms of the natural logarithm. So we can just chuck all those other ones away. Okay, so let's have a look at how this might actually be proved. Can't actually remember off the top of my head, to be honest with you. Oh yeah, it's obvious. Okay, so we can use some of our already established laws of logarithms to help us out here. So let's say we've got a to the power of log to the base a of x. This is equal to x. Okay. So, in fact, no, I'm going to change it. I'm going to have, just to make it more in line with what I wrote earlier, x to the power of log to the base x of y is equal to y. Okay, so we know that is one of the rules that we've already established. So now I can take logarithms of each side of this. I can take log to the base a of x to the log to the base x of y. Equals log to the base a of y. Now, using the law of logarithms, that again we've already proved that log to the base a of x to the power of n is equal to n log to the base a of x. We can use that here to write this as log to the base x of y times log to the base a of x is equal to log to the base a of y. Okay, and therefore log to the base x of y divide through by log to the base a of x. Now, okay, yeah, we're kind of assuming that x is not equal to 1 here, otherwise we can't really divide through. So ignoring that, there are certain technical conditions that we might need to impose on this, but we'll just kind of overlook those for the time, just to get to the point of the argument, really. Log to the base a of y over log to the base a of x. And there we go, change of base rule. And a particular case of this, is the following, that log to the base x of y is equal to log to the base log to the base y of y over log to the base y of x. Now, log to the base y of y is just equal to 1. Log to the base y of x in the denominator. Okay, so in other words, I can change, I can alternate, I can, what's the word that I'm looking for? I can replace x with y and y with x. I can interchange, that's the word that I'm looking for. Interchange the roles of x and y, the base and the exponent. No, it's not the exponent, sorry. The x and y. I can interchange the x and the y. But it comes at a price. Okay, so I get the reciprocal. Okay. Easy. So there's some of our laws of logarithms that we've established. And there's all sorts of stuff that you can go on to do with logarithms. But I think that's about it for this. There's not really anything else that I think I want to cover. So, well, okay, there is actually something else. At some point in your A-level course, what you will prove is that the derivative of the natural logarithm of x, so d by dx of the natural logarithm of x, for example, is 1 over x. Now, most people at A-level will just take this for granted. They won't question this, which is not mathematical at all. As a mathematician, really, you should be questioning why is the derivative of natural logarithm of x equal to 1 over x, and how do we know? So there's different ways that this can be established, but another thing that you will come across at A-level, which won't be proved to you. Again, this will be proved when you get to university, is that you'll see this formula, for example, dy by dx, in fact, I'll write it as dx by dy. So dx by dy is equal to 1 over dy by dx. Okay. So why could this be useful to us? Well, if we've got, for example, y equals e to the power of x, then we can also say that x is equal to the natural logarithm of y. Okay, so if we take this x equals the natural logarithm of y and we differentiate each side of this with respect to y, we get on the one hand dx by dy equals d by dy of the natural logarithm of y. But dx by dy is 1 over dy by dx. Well, what's dy by dx? Dy by dx is equal to e to the x, which is equal to y. So dx by dy is 1 over dy by dx is 1 over y. And therefore the derivative of the natural logarithm of y with respect to y is 1 over y. So again, kind of interchanging the roles of x and y, what we get is that the derivative d by dx of the natural logarithm of y is equal to natural logarithm of x. Sorry, what have I written there? That's terrible. Natural logarithm of x is 1 over x. Okay, get it right, John. Okay, so this result here, to establish this, again, it's not difficult really. It's just you need to know, just as before, you needed to know about continuity in a more thorough kind of way. To establish this, you need to know about differentiability in a much more precise sense. University, you'll do it. You will have to do continuity and differentiability in a lot of detail at university. Don't worry about that. So this result will be proved to you. But at A level, you just kind of introduced to it. Again, if you do want me to go through stuff like this in another video, I can do. Be prepared, it will go into some detail. But if you're into that kind of thing, then by all means, you know, I want to help people as much as possible. I really want to, you know, encourage people to develop their understanding of mathematics. So if it is something that you want to know more about, just let me know. Okay, so we've got a lot of the properties there of logarithms. Now, I mentioned earlier, I'm not going to go through this in detail. I mentioned earlier that it is possible for us to start with logarithms, to define logarithms, and then figure out what we mean by exponential, so we can kind of go in the opposite direction. How might we do that? So I'm going to briefly touch on this. I'm not going to go into detail on this. One way that we can do this is we start out with a definition of a function that we call the natural logarithm. And don't misunderstand me. This is not a random definition. This is motivated by how we want logarithms to behave and the kind of relationship that we want logarithms to have to exponentials. So this is not a random definition, okay? Even though we could arguably define natural logarithm of x in any way that we wanted, we want it to have specific properties. And we want it to be related to exponential functions in a very specific way, okay? So the definition is as follows. The natural logarithm of x is equal to, and there's two parts to it, the integral from 1 to x of 1 over t dt for x greater than or equal to 1, and minus the integral from x to 1 of 1 over t dt for x, let's be a bit more careful here, for 0 less than x less than 1. Okay, so we can define the natural logarithm in this way. From this we can show that this function, the natural logarithm of x, has all the usual properties. So we can show, for example, that the natural logarithm of x times y is equal to the natural logarithm of x plus the natural logarithm of y. I'm not going to go through it in this. But also we can show that this function has an inverse function, and that inverse function satisfies all of the kinds of properties that we associate with an exponential function. Okay. In other words, it really doesn't matter which way we go, whether we start with exponentials and go for then derive logarithms, or if we start with logarithms and derive exponentials. It really doesn't make any difference. I'm going to leave that. Again, you want me to go into more detail on this, I'll do it in another video. So this has already been kind of long enough. But hopefully you found something interesting in this video. If you do like these videos, please show your support for this channel by hitting the subscribe button and hitting the like button. I don't make any money from making these videos. I make them because I want to make them and I want to help people. So if they are helping you, please let me know so that I know to continue making them. Because if I feel that they're not helping anybody, then there's no point in me making them. So if you want me to continue making these videos, let me know. If there's anything that you think that I could be doing better with the videos, because at the minute I'm just kind of making the videos I'm making videos that I think I would have found useful and helpful and interesting when I was doing my A-level maths. So in other words, I'm kind of making these videos for a past version of me. But I really want to be making these videos for current A-level students, to help current A-level students who may have very different needs and wants. Okay, so if there is anything that you would like to see in my videos, if you would like to see my videos done in a different way, I can't necessarily say that I will be able to accommodate every request. But I'll certainly take it into consideration, and it would be greatly appreciated. If you know anybody that would benefit from these videos, please feel free to share them. If you have any comments, if you have anything that you'd like to add, anything that I haven't fully explained in this video or not explained clearly enough, just leave a comment in the comments section. I'll be happy to help out, happy to answer your questions. But hopefully I've explained some things in sufficient detail. Hopefully I've helped you to understand logarithmic functions a little bit better. So I'm going to leave it there for this video. Thanks very much for watching, and I will look forward to seeing you in the next video.